everyone to today's workshop on OptiPress Innovating the Future of Pressure Sensing with the Light, organized by Department of Mechanical Engineering, the Oxford College of Engineering, Bangalore. I am Anup, Faculty of Mechanical Department. I welcome the Chairman, Oxford Group of Institution, Sri SNVL Narasimharaju, Principal Dr. N. Kannan, Head of the Department, Dr. Matsudan Reddy, ISM members, faculty, and students. We have with us Speaker of the event, Dr. Yashaswini PR. Being an eminent personality, she has done remarkable in the field, and we are proud to have her with us today. So, Dr. Yashaswini is an assistant professor in the Department of Electronics and Communication Engineering, Malnad College of Engineering, Hassan. She has 4 years of research experience and 2 years of teaching experience. She has completed the Bachelor of Engineering degree in the Department of Electronics and Communication Engineering from Government of Engineering College, Hassan, under VTU, and Master of Technology in VLSI Design. And she has completed PhD in Design and Performance Analysis of Photonic Sensor for various applications from Malnad College of Engineering, Hassan, under DST Fellowship. She has published several papers and having knowledge of various software platforms such as COMSOL, Multiple Physics, OptiFTD, and ANSYS Numerical, etc. So I welcome you, ma'am.
Thank you, sir. Thank you so much.
So we
Thank you
can
for the
start.
wonderful introduction as well.
Thank you.
Yes.
You can start now.
Thank you. Yes. Yeah, I'll start it. Good morning, everybody. So today I'll be giving a talk on design and performance analysis of photonic crystal-based pressure sensors. So here, so you can, coming up to the details, what you can expect is knowing the basics of photonics, photonic crystal configurations, defect engineering, and also stepwise design of actually 3 different pressure sensor for different applications for different needs. So first thing is, what is photonics? So photonics, it's a combination of the word photon and electronics, and it can also be the science and application of light. Photonic applications, it uses photons in the same applications starting from lasers to photovoltaics, light emitting diodes, integrated photonics. So photonic sensors are one among the greatest applications of photonics. So in today's session, we'll be seeing the design of a photonic crystal based pressure sensor. So coming to the basics, photonic crystals. So what photonic crystal is they are the periodic dielectric nanostructures that manipulates the propagation of electromagnetic waves. And also coming to the pressure sensors, so photonic crystals, they can be used for the design of various sensors like pressure sensors, biosensors, temperature sensors, and the list goes on. So coming to the pressure sensors, here the photonic crystals will be integrated with the moems. Well, moems are nothing but micro-opto electromechanical systems, and these are the systems with structure in the micro to millimeter range, whose purpose to manipulate the light, which has the ability to sense, control, and actuate on the micro scale and generate effects on the macro scale. It has the ability of sensing in micro scale, and the effect will be in the macro scale. So next, coming to the types of photonics crystals. So they are basically created by a periodic arrangement of dielectrics in certain directions. So in first figure, we can see that in the one-dimensional photonic crystal. So we can say that the green box, it is a layer dielectric A, and blue box is dielectric B, which is periodically arranged in certain fashion. Depending on how many axes do have placement dialects, our photonic can be of the type one-dimensional, two-dimensional, and three-dimensional. So all the three you can see in the diagram there. So coming to the photonic crystal configuration, so there are basically two types of photonic crystal configuration. One is rods in air and the other one is holes in slab configuration. So in the rods in air configuration, rod-like structures are created on the photonic crystal in order to form a waveguide. And also in holes in slab configuration, instead of rod-like structures, holes are created on the photonic in the photonic crystal in order to form the waveguide. So basically, these configurations are used to create the waveguide. Coming to the defect engineering, so it is an important concept in the photonic crystal design, structure design. So basically, this is used to manipulate the photons in certain direction, or you can say that we can control the propagation of photons in proper direction. So it is basically used to get the structure that we want, whatever the structure that we select. In order to prepare that structure, we will be using the defect engineering. So in that defect engineering also, we have point defect and line defect. So point defect is nothing but it in figure 2a we can see that. So it is creating a defect by removing a single block or single hole or rod from the crystal, replacing that single hole or rod with another one whose size, shape or the dielectric constant is different from the remaining holes or rods. So similarly, line defect is nothing but instead of a point, the entire line will be removed, or the entire line will be replaced by the different structure of rods and holes. So this is the defect engineering. By using this, we can create the structure that we choose to our particular application. So coming to what are the things that we are going to discuss based on the what are the things that is going to be discussed based on the design of pressure sensors? Is one is an optical MOEMS based photonic crystal pressure sensor diaphragm design is proposed. So then we have, that is for megapascal range. So here three different pressure sensors are shown. So one is for 0 to 6 megapascal, that is first one. And the second one is we are going to see the performance of photonic crystal based resonator structures for ring and the triangular pressure sensors. So it is for gigapascal range. So here we have taken the pressure from 0 to 3 gigapascal. So next, another pressure sensor is designed. It is designed for the detection of barometer application. A pressure sensor is designed. So these are it is in kilopascal range. So for 20 kilopascal range. So basically, all the three different pressure sensors. One is in a megapascal. In another pressure sensor is to detect a pressure of gigapascal range, and the other pressure sensor is to detect the pressure in the kilopascal range. So all the modeling and all these pressure sensors modeling and simulation, it is done using FDTD and FEM tools. So coming to the steps of the designing of first one, that is photonic crystal based pressure sensor from 0 to 6 megapascal range. So the steps for designing, it is same for all the pressure sensors. So first we have to take the design parameters. So what are the design parameters that we have to select? So first design parameters should be defined. So then we have to create the structure using ANSYS tool. So it's a mechanical model. A mechanical model can be first created using ANSYS. In that creation, in the structure, we have to take the consider the circumference as the fixed support, so that one diaphragm will be fixed first, and then pressure will be applied at the center. So circumference is considered as the fixed support. Then the pressure is applied at the center of the diaphragm. So when the pressure is applied at the center of the diaphragm, when it deflects, it will show some strain, stress, and also the displacement. So all these things, that is stress, strain, and deformation, will be tabulated. After that, RI values of for stress values, we have to calculate from the stress values. We will calculate the RI values using a few formula. So then the equivalent mean structure created using the MEEP tool. So use those RI values in the MEEP code, and we have to map that pressure. That is the RI values that we have calculated. If we give it in the, I mean, for holes, if we give that RI value, so that means that particular is applied for particular structure. So here we can use different AVT tools. So we can use MEEP, we can use COMSOL, we can use numericals. So there are OptiFTTD. We can use various softwares here. Next, after that, we have to tabulate the output graphs and the output flux values. So once that is done, the resonant wavelength shift, quality factor, sensitivity, so the output parameters are then computed. So this is the steps for designing any photonic crystal based pressure sensor. So first structure that I have considered is hexagonal ring resonator. So this is done using MEEP. So first one ring, I had tried it for one ring optical ring resonator. So then the work is extended for the double and triple ring resonators. So here these are the design parameters that I have considered for the hexagonal ring resonator structure. So this is the sketch of the 2D design of one ring, two ring and three rings in the ANSYS software. So here it is without the thickness, that is silicon thickness is not yet given in this particular diagram. So we have to give the silicon thickness of 220 nanometers. So here the thickness of silicon diaphragm from the second point, you can see that it is 0.22 micrometer. So some thickness will be given to create that 3D structure. We have to give this thickness. So this is the one ring, two ring, three rings with silicon. So after that, model circumference is that it is a fixed circumference is fixed and so these are the ANSYS results. So that is deformation, stress and strain in all directions. So basically for the calculation of effect we consider only. So this is for one ring, two ring and three ring resonator. So RI value here we can calculate the RI values from the stress values given by using these three equations. We can calculate the refractive index values. So this is the calculated refractive index. So actually for three, I mean one ring, two ring and three ring from 0 megapascals, we have calculated the RI value for one ring, two rings and three rings. So this is the MEEP results, that is the resonant wavelength shift or the transmission graph. For different operators, we have different kind. It is for one ring, two rings and three rings again. So by using this transmission spectrum, we can identify the parameters, that is quality parameters like performance parameters like quality factor, sensitivity. So by using these graphs, so also we can calculate, or directly in MEEP it will be directly given. So here you can see the MEEP results which includes amplitude, wavelength and wavelength shift for one ring, two ring and three rings. So here why this is done, because to show that some wavelength is getting shifted. So basically the sensors, photonic crystal based sensors, it works on the principle that when the change in the refractive index, when there is a change in refractive index, it also gets shifted. So based on that resonant wavelength, identify how much pressure is given on, how much pressure is applied on that particular dial. So we can calculate the sensitivity and the quality factor by using these equations. So here the sensitivity, maximum sensitivity obtained is 550 nanometer per RIU and the Q factor obtained is 12,245. So here you can see the results of one ring, two ring, three ring structures. Both the quality factor and the sensitivity is tabulated. And also here these structures are referred from referral paper. From that paper, we can see that the quality factor was around 2000 there, but the quality factor in our work it is increased exponentially. So then the same structure, hexagonal structure, so I had some design using in MEEP tool, it was quality factor was around 12,245. So the same structure, the design and design parameters are modified, and I have done the analysis of by changing the radius of the holes. I have varied it from 130 nanometer to 145 nanometer. So, and I have got the maximum values of quality factor at 138 nanometer radius of holes. So at that particular value, I have got the quality factor of 15,083. So, and this is the graph of intensity versus radius of the holes. So this is the graph of output spectra at the backward drop port. So from this, we can say that by changing certain parameters or by changing the structure of the design, we can improve the quality factor. So the second pressure sensor here is it is to sense the pressure in the gigapascal range. Here we have designed for a ring structure and a triangular structure both. So these are the design parameters, and this is the field distribution, that is how the light is resonating in both the ring and the triangular resonator. So this is done using the ORSOFT tool. Similarly, so first one is done in MEEP, second one which I had explained, I had done it in numericals, and this is using ORSOFT tool. So this is the transmission spectrum for the ring resonator, and this is for the triangular resonator. We can observe the normalized power with respect to wavelength for different values of pressure. So from 0, 1 gigapascal, 0.5, 2.5, and 3. So these are the pressures that are tested for. So here has been here. So we have the least quality factor is 153 and the maximum quality factor is 1634. So hence we can say that the ring resonator works well for the pressure range from 0 to 2 gigapascal range. And also from the table 16, this is the referral paper table. So the quality factor is very low actually. So in our work it is improved. So from this table, table 15, we can say that from 0 to 2, for 0 to 2 gigapascal range, we can use the ring resonator structure. That is ring resonator, it works well compared to triangular resonator. So this is for the triangular resonator structure. So here we can see that the quality factor, it is varying from 800 to 1845. So that means that here it is working well. So sorry, here it is in the for the ring resonator, we can see that so maximum Q factor it is from 1634 to 1634, but the maximum Q factors we are getting here from 2 to 3 gigapascal actually. From 2 to 3 gigapascal, the Q factor is highest. We can see from the table. So from 2 to 3 gigapascal, ring resonators works well. So in the triangular resonator, we can see that the maximum Q factors, it is from 0 to 2 gigapascal. So for 0 to 2 gigapascal range, triangular resonators works well, and 2 to 3 gigapascal range, ring resonator works well. So next is the crystal ring and the semicircular resonator based pressure sensor for the detection of back. This is for the pressure range in the kilopascal range. So basically this barotrauma means when there is an excessive stress on the eardrum because of change in the pressure range. So it causes a issue called as barotrauma. So this is a main issue for the scuba divers and the skydivers when there is a extreme change in the pressure. So what it affects the eardrum and it ruptures the eardrum. So this is actually a quite a big problem for scuba divers and skydivers. So for that case, if we can easily detect the pressure in kilopascals, so we can prevent the damage to the eardrum. So if there is basically if there is an excessive pressure higher than 20 kilopascals, there will be a damage to the eardrum. So here MOEMS based ring resonator and a semicircular resonator structure are designed to check which one works well for this particular application. So here also we came to a conclusion that the ring resonator structure, it is little less for the compared to the semicircular structure. So this modeling, it is done using a FEM tool called as JCM suit. So here also we can see that the resonator structure for the in 3D for both ring resonator and semicircular resonator. So these are the design parameters that I had considered, and these are the simulation results. Similarly, stress, strain, and deformation values will be there, and then we calculate the amplitude shift and the ring circular design. So here you can see the transmission spectrum for the ring and the semicircular structure. So in the table 20, we can see the quality factor for the ring and the semicircular structure. From this table and also the referred papers, it is quality factor is improved, and also we can come to the conclusion that for the 20 kilopascal range, so semicircular structure works well as compared to the ring structure. So basically, we have in today's talk, we have discussed about photonic crystal based resonator structures for different pressure for different pressure ranges. So that is from for 0 to 6 megapascal range, the quality factor was 12,245 in the MEP structure. Then it is improved by in the numerical software, and the quality factor obtained is around 15,000. So then for the 0 to 3 gigapascal range, we came to know that the triangular resonator, it provides good performance between 0 to 2 gigapascal, and ring resonator, it provides good performance between 2 to 3 gigapascal. And finally, for the application of barotrauma, that is to sense the pressure in the range of 20 kilopascal. So semicircular resonator structure, it works well works well, and it is done using a FEM solver called as JCM suit. These are the references. Thank you. So if you have any doubts, you can ask me.
The mic is allowed for attendees. Anybody having questions, they can ask. The mic is allowed for attendees. Anybody having questions? Anybody was asking question? I can't hear. Okay, we'll end of the session. Anup, on behalf of everyone, thank Dr. Yashaswini PR for very systematically laying the framework on the topic of optical pressure sensors. And it was very nice PPT, ma'am. And it was a very interesting session. And I thank you for accepting and doing this for us. And further, I thank our institute, the management director and principal, Dr. N. Kannan, and head of the department. Also, I thank ISS student coordinators who have been involved in promoting this event. And acknowledge all. Thank you once again to all.
Thank you, sir. I would like to thank Oxford College of Engineering for this opportunity, and thank you, Anup sir, and thank you, Preeta ma'am, for this opportunity. Thank you, everyone.
Yeah.
Thank you.